等特色人才培养项目，致力于培养一批热爱数学、西餐厅品尝美味。求真书院图书馆将汇聚国际数学领域的重要藏书和期刊，为大家的科研工作提供支持。热爱艺术的求真人，可以在琴房找寻艺术的灵感，在合唱室放声歌唱；热爱运动的求真人，可以在健身房、瑜伽室体会运动的乐趣。我们相信，在丘成桐院长的亲自带领下，求真书院将汇聚全球顶尖数学师资和年轻学子，这里也将成为全球数学版图上的一颗明珠，照亮数学科学发展的方向。欢迎加入我们，一起追求数学的至真至美。数学是科学的基础，是人类科技进步的源泉。为了推动全球数学发展，在丘成桐先生的倡导下，清华大学在2021年4月成立求真书院，开设丘成桐数学科学领军人才培养计划、丘成桐英才班、数学与人工智能实验班等特色人才培养项目，致力于培养一批热爱数学、有志于推动全球数学发展的顶尖数学人才。经过4年多的快速发展，求真书院已经拥有完善的本科生和研究生培养体系。在读本科生和研究生分别是420人和130人，稳态时书院的学生规模将超过1200人。顶尖数学人才的培养，不仅需要选拔到第一流的年轻学生，还需要引进一流大师教导学生。更重要的是，一流的学生和一流的老师都需要一流的空间，方能心无旁骛，安心学术。在北京市海淀区，清华大学的大力支持下，清华大学求真书院实体空间将于2026年5月正式建成。求真书院实体空间位于水墨园区，该园区毗邻清华大学，与万远之园圆明园遗址公园隔路相望。这里属于3山5园区域，具有优秀的历史文化资源、深厚的人文底蕴和优美的生态环境，是中国优秀传统文化与新兴文化交融的复合型地区。相信求真书院的入驻，将会为3山5园带来新的资源与活力。求真书院以建设国际一流书院为目标，园区规划紧紧围绕教师和学生需求，汇聚了科研、教学、办公、会议、健身、餐饮等丰富功能。求真书院提供50多套讲席教授公寓，每位讲席教授的生活将在这里得到最好的保障。讲席教授公寓楼下即是办公区，旁边围绕着研究生的办公工位和交流研讨空间，大家可以随时停下脚步交流学术前沿问题。求真书院建设了30多套智能化教室，不出园区，师生即可完成知识的传递。求真书院的每个人可以在菲尔兹咖啡厅驻足停歇，也可以在西餐厅品尝美味。求真书院图书馆将汇聚国际数学领域的重要藏书和期刊，为大家的科研工作提供支持。热爱艺术的求真人，可以在琴房找寻艺术的灵感，在合唱室放声歌唱；热爱运动的求真人，可以在健身房、瑜伽室体会运动的乐趣。我们相信，在丘成桐院长的亲自带领下，求真书院将汇聚全球顶尖数学师资和年轻学子，这里也将成为全球数学版图上的一颗明珠，照亮数学科学发展的方向。欢迎加入我们，一起追求数学的至真至美。
Good evening, distinguished guests. Welcome to Information Science and Engineering 2025 night, where innovation meets legacy and curiosity support transformation. I'm host Rongling Wu. First of all, let me introduce our distinguished guest. President of International Congress of Basic Science, President of Beijing Institute of Mathematical Science and Application, member of U.S. National Academy of Science, foreign member of Chinese Academy of Science, field medalist Xiantong Yao. Professor of Physics at Stanford University, member of U.S. National Academy of Science, Nobel laureate in physics, Steven Chu. Professor of Computer Science at Princeton University, member of U.S. National Academy of Science, Turing Award winner, Robert Andrew Taryan. Vice President of Commercial Aircraft Corporation of China Limited, Mr. Vincent Wu. Chief Scientist of Commercial Aircraft Corporation of China Limited, member of Chinese Academy of Engineering, Professor Guanghui Wu. We also invite 3 representatives of FSA winners. They are Professor Yang Lu, Dimitri Poliskin, Rainer Spricker. Welcome. With great honor, I'm now declare the 2025 Information Science and Engineering Congress. First of all, let's invite Professor Xiantong Yao to set the tone for this great convergence of mind. Welcome, Professor Yao, for welcome speech.
Well, dear participants of ICBS 2025, colleagues and guests, welcome to the Information Science and Engineering Night at the 2025 International Congress of Basic Science. We gather as practitioners and innovators to advance the application of basic science in the engineering fields. Today's theme, Information Science and Engineering, represents the convergence of disciplines where mathematical rigor, engineering systems, and artificial intelligence interact. This synthesis drives modern scientific progress and redefines technological frontier. We convene at BIMSA, an institute dedicated to interdisciplinary collaborations. Our speakers, Professor Steven Chu, Professor Robert Targan, and Professor Guanghui Wu, will present critical insights spanning fundamental science and applied innovations. Subsequent discussions will address challenges and opportunities unique to this integrated domain. We would like to acknowledge COMAC,商飞, for your continuous efforts to this event. Your leadership in the large-scale engineering mirrors our commitment to fundamental research that bridges theory and practice. The ISE night includes academic discourse, technical demonstrations, and collaborative dialogue. May this evening inspire enduring partnership across our disciplines. Thank you.
Thank you, Professor Yao. Let's invite Vice President of Commercial Aircraft Corporation of China Limited, Mr. Wensheng Wu, give us a VIP speech. Welcome.
"尊敬的丘成桐院士、朱棣文院士、罗伯特·塔扬院士、吴光辉院士，各位科学家朋友们，大家下午好。
Distinguished Academician Xing-Tong Yao, Academician Steven Chu, Academician Robert Taiyan, Academician Wu Guanghui, fellow scientists and friends, good afternoon.
1年前的今天，在数学博物馆，贺东风董事长与邱先生共同见证了雁栖湖应用数学研究院与中国商飞战略合作的签署。雁栖湖的数学家与中国商飞的科学家、工程师们围坐在一堂，共同探讨如何用数学的力量、基础科学的突破来撬动大飞机科技创新的杠杆。
1 year ago today, at the Mathematics Museum, Chairman He Dongfeng and Mr. Yao witnessed the signing of the Strategic Cooperation Agreement between the Yanqi Lake Institute of Applied Mathematics and COMAC. Mathematicians from Yanqi Lake and scientists and engineers of COMAC gathered together to discuss how to leverage the power of mathematics and breakthroughs in basic sciences to drive technological innovation in large aircraft.
在过去的1年中，邱先生带着数学家们走进我们的 C919 大飞机研制现场，深入了解大飞机产业的核心需求，更引荐了包括尤瓦尔·佩雷斯、张晓明、乌荣岭、龙飞、蔡云峰、杨武岳在内的一众顶级科学家加入大飞机研发阵营，围绕大飞机控制、空气动力学设计、飞机健康管理等关键领域开展了一系列突破性的探索。而今天，当朱棣文院士这位在能源科学领域深耕多年的大师莅临现场，更让我们看到了基础科学与工程实践碰撞出的无限可能。当罗伯特·塔扬院士这位在人工智能领域的大师坐在我们身边，让我们进一步去探索和尝试如何用人工智能重塑我们的航空工程。
Over the past year, Mr. Yao has led mathematicians to visit the C919 development site, gaining a deep understanding of the core needs of the large aircraft industry. He has also introduced a group of top scientists, including Yuval Perez, Zhang Xiaoming, Wu Rongling, Long Fei, Cai Yunfeng, and Yang Wuyue to join the large aircraft R&D team. They have carried out a series of breakthrough explorations in key fields such as aircraft control, aerodynamic design, and aircraft health management. Today, the presence of academician Steven Chu, a master with years of dedication to energy science, further shows us the infinite possibilities arising from the collision between basic sciences and engineering practice. The presence of academician Robert Taiyan, a master in artificial intelligence, encourages us to explore and attempt how to reshape our aviation engineering with AI.
展望未来，中国商飞将以更大的诚意、更实的举措，深化与基础科学界的合作，特别期待在航空减排技术领域开展深度攻关，从新型环保航空能源到飞机气动的优化设计，让绿色飞行的愿景照进现实。同时，在智能系统领域持续发力，推动大飞机全生命周期的智能升级。我们将聚集气动布局优化、结构轻量化设计、智能运维等关键领域，让科学家们的创新思想在工程实践中充分绽放。我们还将继续支持数学家、工程师跨界交流，让基础科学的火种在大飞机事业中燃烧绽放。
Looking ahead, COMAC will deepen its cooperation with the basic science community with greater sincerity and more concrete measures. We particularly look forward to conducting in-depth research in aviation emission reduction technologies, from new environmentally friendly aviation energy to optimized aerodynamic design of aircraft, so as to make the vision of green flight a reality. At the same time, we will continue to make efforts in the field of intelligent systems to promote the intelligent upgrading of the entire life cycle of large aircraft. We will focus on key areas such as aerodynamic layout optimization, structural lightweight design, and intelligent operation and maintenance, allowing scientists' innovative ideas to fully bloom in engineering practice. We will also continue to support cross-disciplinary exchanges between mathematicians and engineers so that the spark of basic sciences can burn and bloom in the cause of large aircraft.
邱先生常说，数学是科学的语言，而我们坚信，当这种语言与朱迪文院士的基础物理能源科学智慧相遇，能破解大飞机绿色发展的密码。与罗伯特·塔扬院士的计算科学成果结合，能打开智能航空的新空间。吴光辉院士作为中国民机的领军人物，在过去的相当长一段时间里，引领我们共同去思考和探索如何使用人工智能技术提升商业飞机的设计水平。
Mr. Yao often says, mathematics is the language of science. We firmly believe that when this language meets the wisdom of academician Steven Chu in basic physics and energy science, it can decipher the code for the grain development of large aircraft. When combined with the computational science achievements of academician Robert Taiyan, it can open up new space for intelligent aviation. As a leader in China's civil aircraft industry, academician Wu Guanghui has for a long time led us to think and explore how to use artificial intelligence technology to improve the design level of commercial aircraft.
当这些基础科学的光芒汇聚到大飞机的工程实践中，必将书写出更多的从0到1的创新故事。让我们以雁栖湖为新起点，用基础科学的力量托举大飞机飞向更高更远的天空，为中国航空事业的发展，为世界航空产业的可持续发展共同贡献智慧与力量。最后，请允许我代表贺东风董事长向各位科学家朋友们致最崇高的敬意和最诚挚的谢意。谢谢大家。
When the light of these basic science converges in the engineering practice of large aircraft, it will surely write more innovative stories. Let us take Yanqi Lake as a new starting point, use the power of basic sciences to lift a large aircraft to fly higher and farther, and jointly contribute wisdom and strength to China's aviation industry and the sustainable development of the global aviation industry. Finally, on behalf of Chairman He Dongfeng, I would like to contribute my highest respect and appreciation to all the scientists and experts here. Thank you.
Thank you, Mr. Wu. Ladies and gentlemen, this ICBS provides us with many desirable opportunities to listen to great voice, tonight we are fortunate enough to invite Professor Steven Chu to give us a keynote academic speech. How does biology works in a world dominated by Brownian motion and friction? Welcome, Professor Chu.
Let me just do what I have to do here. Put this in here. And is that? And is this power? This for H. Okay. Okay. And do I see? Great. Okay, so first, I have to say that I'm not formally dressed anymore. There's only several days in a row I can wear a suit. Although I spent 4.5 years wearing suits in DC, because if you don't wear a suit, they think they don't respect you. But be sure I respect all of you. Anyway. What I want to talk to you about is some biology, but it's not really biology. I hope to convince you that it's moving very rapidly towards real physics. And by physics, I mean, and I can't go into details, but one can form mathematical models of what the biological mechanisms are, and you can test those models with experiments. And that's the key. Quantitative science, you make falsifiable predictions. So I'm going to talk about statistical physics at the molecular scale, but primarily about how molecular motors work and in cells, how molecular motors work and they might work in cells. As I said in my random walk talk, I was quoting Erwin Schrödinger, his Life Based on the Laws of Physics, in What is Life? And he said, from all that we've learned, let me remind you, about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to ordinary laws of physics, not because there's any new force, but because the construction is different from anything we have yet tested in the physical laboratory. And so the issue, again, to remind you, is molecular machinery is embedded in very, very strange things that we're not used to in the macroscopic world. For example, F does not equal ma at the molecular scale in the biological world. If force is not proportional to acceleration, with the constant being mass, but force is proportional to viscous drag, and that constant is, let's say, Stokes drag. And in addition to that, these things are always jiggling around due to Brownian motion. Smaller it is, the more Brownian motion there is. And so one has to ask the question, how is it possible to imagine machines working in this environment of huge Brownian motion, huge viscous drag, huge friction? And is it possible that biology at the molecular level can actually exploit these fluctuations in ingenious ways? But before I do that, since you're not biologists, I need to introduce you to a little bit of what molecular motors is about. And I'm going to use a short movie made by a colleague friend of mine, a biologist named Ron Vale. So I don't know if...
Just like a busy city, there's constant motion inside of your cells. There's new construction, demolition, and most importantly, transporting goods from one place in the cell to another. Cells transport goods along cellular roadways. To transport cargo along these roads, the cells use motor proteins. Kinesin is one of these motor proteins. If you didn't have kinesin and other motor proteins, you simply wouldn't be alive.
All right, so that's an introduction to kinesin, and in this work that I was going to briefly describe, I'm not going to talk about kinesin, but I'm going to talk about a related motor called dynein. This is a schematic picture of a neuron. This is the body of the cell, and a long, thin axon, maybe just 5-6 microns in diameter, then stretches all the way to over here, where these little axon pieces will then form connections to other neurons. Now, a lot of the stuff is made in the body of the cell, but you need a lot of energy, for example, over here. And so the motor kinesin will take the organelle, the small thing in the cell that actually makes ATP, and moves it along this to down here where the energy is needed. And so, and there's other things like organelles, and so kinesin goes this way. But in addition to that, there are chemical signals of this neuron that get received through its connection to other neurons. Those chemical signals have to be transported back to the cell because they're very crucial chemical signals. If they're not there, the neuron would kill itself because it thinks that something is wrong. I don't have good connections in so-called synapses, so it will die. And that, for example, nerve growth factor is an essential molecule for this transport in the other direction. Okay, this is a very complicated motor. It's the most complicated molecular motor we've been studying in biology. It's called dynein. It's a very, very big, it's got a mass of 1.5 million hydrogen atoms. Now, how do these motors work? Well, there's this fiction of how a motor might work, like a machine, just plodding along, stepping. You may have also seen these motors like that. And this is a true fiction. It's the imagination of a movie maker biologist type who thinks that it looks like a macroscopic machine. It does a very orderly, stepwise production. A Ron-Veil simulation is a little bit more realistic. In the case of dynein, they have 2 legs. So these are the 2 legs of dynein. And let me show you his version of how this thing works. The music is very important in this molecular scale. So that's 1 leg, and you see that red thing, it's called the linker arm. It bends, and this, while it's searching around for a new landing spot, it finally lands, searching around now on the other leg. And then when it lands, you'll see it land. And when it lands, this red thing straightens out and goes into a new position. And when it straightens out, the cargo vesicle carrying the chemical information can move. And so in our setup, we have immature neurons over here. There's a microfluidic cell. You can actually buy them commercially or make them. It doesn't really matter. And then this little channel is maybe 10 by 10 microns in size. And the neurons can be induced to grow across here. And then what we do is we put probe particles, for example, upconverting nanoparticles that we synthesized, learned how to synthesize them better than previously by about a factor of 10 or 20 from the previous workers. They're very bright, and they get picked up by the cell. And on the surface of these nanoparticles, we fool the cell into saying there's a chemical protein that says, transport me back to the cell body. So the cell does all the hard work. It puts these particles into a little cargo vesicle. It puts all the motor proteins on, and it starts moving it back to the body of the cell. And so this is an example of some raw data taken maybe a half a dozen years ago. We only see the nanoparticle because we're exciting in the infrared. The cell doesn't have any luminescence in the infrared. And so we're not damaging the cell with infrared light. And you see sometimes it gets a little confused, goes backward. In a moment, you'll see it go backward. And we saw it go backward a little bit while before. Now it's going to go backward, but it's actually changing tracks. And so the resolution of this going backward towards the retrograde means we're going backward towards the cell body. And in that little movie you saw, it went its way, it went backwards. And you might think, what's going on? I thought this motor is designed to go from the exterior portions of the cell and bring it back to the cell body. But in actual fact, biology wants to conserve a lot of things. The motors that take cargoes to the distant axons sides where the synapses are have to be transported back, because if you don't transport them back, you've just lost it, you throw away the motor. So in the trafficking of the motors, both motors are actually on this cargo and walking on the so-called microtubules, the little roadway tracks. And so when it goes back, we think it's the signals are being confused biologically and it loses track of where it's going, but it fixes itself and goes backwards. Okay. So normally I would talk about many, many things, what we discovered on long-term tracking. We discovered, for example, that the model suggested in 2006 by Ron Vale and his colleagues, we found did not agree with our data. Then we looked, because it was COVID time and all we could do was kind of read papers for a while. And so what happened is I did something I rarely do. I read the entire literature with my postdoc Sam Pang and the supplementary materials many, many times. And we found that even ironically, the supplementary materials of some of these papers disagree with the body of the material. I think that there was too many authors in some of these papers. And what we found is that the model we had, which uses 2 ATPs instead of 1 ATP, ATP is the unit of fuel in biology, adenosine triphosphate. The fuel is supplied by breaking a phosphate out and the chemical energy is released. And what we found is it uses 2 ATPs, not 1. And so it's contrary to accepted models. And this is both good news and bad news. It's good news because it's a surprise. It's bad news because there is an existing model, therefore it takes 3 more years to get it published. Anyway, I'm not going to go through any of this. I'm just going to focus on one thing, statistical fluctuations. And so let me take you to where the current understanding of this motor dyning was. You saw those 2 legs walking and that linker arm being bent. And so in various stages of ATP hydrolysis, lots of things have been ascertained by other researchers, not us. But the crucial thing is when this motor linker arm decides to come back down here and it goes from this position to this position, it's so-called power stroke. That power stroke moves this cargo, indicated schematically here, from this old position to the new position. And so the question is, and so I start asking the molecular biologists who formulated this model, where does the power stroke come from? We know the structures at certain stages of this motor. We know a lot of the chemical kinetics. And they say, well, we don't really know, but we're sure there has to be a power stroke. And so the question is it really a power stroke or is it due to something else? As a newbie in the study of dyning, I get to ask that question. But I also get to ask a simple question as a physicist. Suppose there is a power stroke. Suppose this arm does suddenly come down here. As it suddenly comes down here, this attachment to this cargo is some spring of some kind. It could be a linear spring, it could be a nonlinear spring, it doesn't really matter. But let's take the simplest case of the move in distance is attached to a linear spring. So the spring is modeled as a spring constant times x. But then this thing has to move, but it's moving through viscous drag. The viscous drag is actually given by Stokes drag and the velocity. As I said, that's the new Newton's law. Well, this is a differential equation everybody can solve. There's x over delta x, and you solve it, and you find that if there's a sudden power stroke and it's a linear spring, the relaxation is independent of the step size. Now, if it's a nonlinear spring, okay, it's slightly different than that, but fundamentally, it's going to, you take a big step, you take a small step, and the cargo just moves roughly independent of the step size. Okay, so that's one view. I say no. How about another view? Suppose this is one of the legs of the motor. It's about to take a step. ATP lands on it. We know when ATP lands on it, this binding spot here, it's bound here. The link arm is bound here. It's designed to be very flexible. You can look at the structure, and it's actually just a little flexi point, and it's bound here. If ATP lands on it, we know that this binding spot disappears. It's released, but it can be released and found in many states. It could be slightly bent like that. It can have a big bend like that. It can have an even bigger bend like that. So imagine if it's in this state, looking around, searching around for the new spot to land, okay? It's doing a Brownian motion search. And suppose it goes from, it makes a big step or a small step. Okay, if the linker arm is making a small step, it doesn't have to diffuse as much. But we know from diffusion that if there's no potential weld, the diffusion time, statistically averaged, goes as a square of the distance. If there's a slight potential, it would have a slightly longer time. And so that gives you an immediately falsifiable prediction. If the step size is big, it should take longer to go from one position to another position. If the step size is small, it should be faster. And so we said, okay, this is pretty interesting. Small step, you have to Brownian walk diffusion. It's a Brownian walk diffusion to first arrival time, where it gets close enough to rebind, allowed by the ATP hydrolysis, right? Big step, it has to walk longer. So surprisingly, in this model, we started looking at the literature, and we found a really pioneering paper, but it was a strange paper because it was done by Sunny Shi, who's now at Peking University. Xiaolin Nan was the graduate student who did the work, who later worked with me as a postdoc and is now doing cancer research at Oregon State Health University. And they only made 3 measurements of the transition time between one position and another position. A 20 nanometer step, it took a half a millisecond. An 8 nanometer step, 120 microseconds. It's depending on the step size, but there are only 3 data points. So this is no good. It's a statistical measurement. And in fact, if you make thousands and thousands of measurements, you can probably unpack the shape of the potential as well. So we said, okay, we're going to make a better apparatus. And so the idea of this apparatus is the following. In this animation, you have this particle that's scattering light. The light is collected in an optical microscope and is used as a knife-edge mirror, and some of the light goes to one photodiode and the rest of the light goes to the other photodiode. So if this particle moves, let me play the animation over again, you can see that the amount of light going to one photodiode and the other photodiode changes. What you do then is you put these 2 photodiodes onto a differential amplifier and you measure what happens. Now, we start to depart from, Xiaolin Nan actually used this, and Shanishi used this method, but they used visible light. They used a plasmonic nanoparticle, a gold particle. But if you actually go and make a shell instead of a gold nanoparticle, we don't even have to make the shell. These are commercially available. What you find is you can get a size of nanoparticle that easily gets swallowed by the cell and transported back, but the resonance is around 800 nanometers. 800 nanometers is a magic wavelength. 960, our old particles, was warming up water. If you're at 600, 500, 700 nanometers, the visible light is making reactive ion species that slowly is killing the cell. And so either you're heating up the cell or you're killing the cell, but at 800, 840 nanometers, you're not doing anything. So we can pour on a lot more light. We can look, as we did in the first experiment, by tens of minutes on a single neuron as it makes this distance of a 1 meter track. And so, but where's the problem? There's a technical problem. It's a small one. It's a plasmonic particle. It means it scatters light elastically. one frequency in, same frequency out. If you have elastic scattering and you have direct specular reflections, you're going to be swamped by scattered light that you don't want to do. So what you do is you design an optical system. So these blue thick arrows are little cones of light coming in, but you only accept light in a smaller narrow cone, so the direct reflection goes back here and the light from here goes back here, and you miss all that stuff. And so this little trick is called dark field microscopy. It's well known to microscopists and actually even to material scientists. So we use that. We want really good spatial and time resolution. So the microscope can't be a normal microscope. By far it can't be. In fact, what we found is unless we made something that held the microscope objective extremely rigidly, you could see all sorts of vibrations and stuff you don't want to see. So this doesn't really look like a microscope, and it's just used to hold the microscope objective. And so it works well. We now have, before we had a spatial resolution of noise of 4 nanometers in 1 millisecond averaging time. And now we have a spatial resolution of 0.13 nanometers, 1.3 angstroms in a temporal resolution of 1 microsecond. So it's a bunch of orders of magnitude better than our previous work and a couple of orders of magnitude than anybody else's work. And we're beginning to see, guess what? All sorts of strange stuff we didn't see before. So we need to put it through this calibration, but it's very exciting. So this is the low noise, and you say, well, what about all that stuff? That stuff is acoustic noise. The stuff we were doing is very rigid, and we don't see that. So there's acoustic noise, and we have to shield out the acoustic noise. So we're building prototype acoustic isolation systems to surround the microscope. This is Jeremy Axelrod, the postdoc working on the experiment, being acoustically isolated. Okay, so that's where we are. We're pretty confident we can get the acoustic noise down by a couple orders of magnitude, maybe 1 or 2 at least. And so it will be by far the best, highest resolution scanning microscope for live cells. Now, I do want to talk about one last thing, and that is non-equilibrium statistical physics of dining. And so there's a new theorem in statistical physics called the fluctuation theorem. So let me walk you through the idea. If you have 2 molecules and they collide with each other, time is going in this direction. So these 2 molecules come, they collide, and they separate. You can run the movie backwards. 2 molecules come, they collide, and they separate. You can't tell one from the other. Why? Because the fundamental interaction is time reversal invariant, right? Now, suppose you do something different. You take a drop of blue ink and you drop it in there. And now you see their time has an arrow, because all those blue molecules want to say, well, hey, I used to be in a drop, but I can be anywhere in the beaker. So if you wait for a long enough period of time, you'll find after it reaches equilibrium that the blue molecules are everywhere. And what we say is the entropy has increased. You have a much more ordered state where all the blue molecules are close together to where they're all separated. So entropy is increasing. But most of statistical physics is equilibrium statistical physics. There's a new theorem that says we don't have to wait for equilibrium. We look at the probability of entropy increasing going forward in time, divided by the probability of entropy decreasing going backward in time. This theorem says that that ratio is equal to the change in entropy divided by K. K is the constant, that's a historical constant, because we measure temperature in degrees rather than in joules, which should have been measured. So anyway, this is amazing because this theorem states that probably if entropy increasing becomes exponentially larger, so you go back forward in time, but for a very brief instant in time, it's time reversal invariant, right? Delta S is very small, going backward and forward is equal probability. So, but it's amazing. This theorem was discovered numerically accidentally in 1993, not 1893. 1993. It was then proven more rigorously over the succeeding years. And this theorem allows us to watch something move and measure the change in entropy. I don't want to actually go through this, but this is the fluctuation theorem, going forward in time, going backward in time. And what we do is we look at this motor moving something, and we say, okay, at time t, x equals time t, the position is here. At time t plus tau, the position is here. So if you look at the change at time t equals 0, it's over here. At 10 milliseconds later, we look at the record of many, many walks, and it's spread out. 40 milliseconds, spread out further. 100 milliseconds, spread out further. Because of the central limit theorem, you can fit all these distributions over many statistical averages to a mean and a dispersion, sigma squared. And so if I do this and look at this equation, take the logarithm of this side, the logarithm of that side, and that's this logarithm is easy. So you have the log of the probabilities, but this is great because if you have probabilities in the denominator and numerator that are in the exponents, it's just added and subtracting things. So when you do this, what you find is a measurable quantity, how the mean and spread is going, can be related, that's the mean of the Gaussian, that's the dispersion, to a measurable quantity, phi. And I'm not going to go through the math, but I'm just going to tell you something really strange. If you take this theorem, and it is a theorem, it's now proven rigorously, phi is a measured quantity, and you can relate this to a measured quantity of the force over the distance times this, which gives you a force over kT. So you plug in the numbers. And what you find is at 37 degrees, the temperature of mammals, us in particular, that's 310 Kelvin, you find that this theorem tells you that the force is less than or equal to 0.3 piconewtons. A piconewton is 10 minus 12 newtons, small force, but it's a molecule. However, you know the size of the object, you know the viscosity. How do we know the viscosity? You actually put a particle in the cell and you watch it diffuse, a free particle. Just watch it diffuse. So that's measured quantity. We know the size, we know the viscosity, and we plug in the numbers, and lo and behold, we get a force of 2.5 piconewtons. Well, which is different than 3.43 piconewtons. Now, let's suspend belief for a little while and say, what if this temperature is not really real temperature? What if it's an effective temperature? That effective temperature has to be 5.7 times 310 Kelvin. Now, 5.7 times 310 Kelvin is, things get ionized. The cell's dead, your sample's dead, the water's not there, okay? So what does effective temperature mean? We have a beautiful model of it, and what it really means is that vesicle and the motor have jiggling, Brownian motion jiggling, and it's got two terms. It's got one term that's just a normal temperature Brownian motion jiggling of the fluid, and if you move in the frame of reference of the motor goes step, step, sometimes it goes backwards, step, step, step. It's how far it steps, when it steps, has the stochastic variance. If you move in the frame of reference of the motor, and in particular, go back to here, now we're moving in the frame of reference of the motor. In the frame of reference of the motor, what we're seeing is diffusion. Time t equals 0, it's here, and it's a Gaussian, and the Gaussian spreads, the Gaussian spreads. And so how's the Gaussian spreading? Guess what? Turns out it's spreading with an effective temperature 5.7 times the real temperature. It's because the motor is so powerful that it's a statistical variable again, and it just overcomes, it's much bigger than the normal Brownian motion. That's all it is. So the mystery is solved, but it's way better because if it goes faster, it's even better than that. And this started long ago, and I'll take you in the next 2 seconds, or now 2 minutes, to a conjecture by Lars Sonsager in 1931. He said, suppose I have a system and I move it slightly out of equilibrium and I let it go. Sonsager said, the way it approaches back to equilibrium has to be related to its fluctuations about equilibrium. There's a deep theorem called the fluctuation dissipation theorem that says that if you have dissipation, in this case viscous drag, or in the case of a resistor, the dissipation is resistance, and the fluctuations are voltage fluctuations you see in a wire. By the way, the fluctuation dissipation theorem was first conjectured to be there by a Bell Labs engineer, not by Einstein. Einstein finessed it, so he didn't see the deeper connection. And the Bell Labs engineer was called Nyquist at the Nyquist limit. And so another thing about, and anyway, so Onsager said, the approach to equilibrium is related to its fluctuations around the equilibrium. Fluctuations can be measured by a correlation function, and the friction measured by the response of a force. Okay, so about 20, 25 years later, he gets a Nobel Prize for this, because it's the first attempt to take statistical physics to non-equilibrium statistical physics. But in hindsight, as in many things in science, it had to be true. Why? Suppose this thing's fluctuating, and you take a snapshot, you didn't see what happened before, and you put it 4 sigma out. And how do you know I took it, put it 4 sigma away, or a fluctuation took it 4 sigma away? You won't. All you know is its approach back to the norm has got to be the same. So of course it had to be true in hindsight after 30 years or 50 years, or actually nearly 100 years today. And so, but it deserves a Nobel Prize because it was the first attempt to try to take statistical physics away from equilibrium statistical physics. And so it turns out that this is the first physical example of non-equilibrium effective temperature. The previous examples were artificial examples. In fact, the previous examples actually took an optical tweezer and just jiggled something. The optical tweezer provided the stochastic force. But now we find in nature that motor provides the statistical stochastic force, which is very cool. So for the first time, biology is actually giving something back to physics. One last thing, and I'll stop. And I'm going to talk about Maxwell's demon. Suppose there's a little demon and you've got hot molecules and cold molecules, and it wants to separate the hot from the cold. So it sees a hot molecule coming by, it opens a little trap door and lets it go by. But if a hot molecule is going the other way, it keeps it shut. But if it sees the cold molecule, it opens the trap door and lets it go. So the Szilard example of Maxwell's demon is very elegant. He says, consider one molecule in a box, and you slam a partition. But you know where the particle is because you're a Maxwell demon. So let's say the particle is on the left-hand side. So it's bouncing around. After many, many collisions, it begins to push the piston, and so it does work. Okay? Then it's done. You let it, there's no more, you slam down the thing again, maybe you find it on the right-hand side. So it pushes the piston over there. If you didn't have a demon measurement, all you see is the piston jiggling around. But if you knew where it was, you knew which way it's going to push, you can actually extract work. Here's the dilemma. How can you extract work at the same temperature? That violates thermodynamics. Okay? All right. So it violates the second law. You can't do that. All right. Last little bit. Shannon of Bell Labs developed information theory. He wanted to know, is it possible to send in a noisy channel some data so that if there's an upper limit on the noisy channel, he showed that you can reconstruct that message perfectly in a finite amount of time. And what he did was actually the precursor to, completing sentences, which was the precursor to large language models. So Shannon's information theory was actually the precursor to completing sentences. And so what he said was he wanted this information to be additive, so he used something that's the probability times the log of the probability of whatever number of states. Take the simplest, 2 states, it's 0 or 1. And so if you look at this, with Shannon's definition of digital binary 0 or 1, heads or tails, if you flip a coin and before you look, you don't know whether it's heads or tails. And so what's the information in this? the information is 1, because there are two, okay, just do the math, the arithmetic. You look, it's either heads or tails. That information says there's only one state, and since entropy is the number of accessible states, there's only one left, it's 0. So it goes from 1 to 0, okay? And so with Shannon's information theory, he develops this whole idea of, well, information theory. And so Leo Szilard, so how's this related to Leo Szilard's Maxwell Demon? He said, well, before you look, when you look, you've changed the entropy. And so here's the big gigantic leap. You take the normal thermodynamic energy, which is the number of accessible states times Boltzmann's constant, and that's the Boltzmann energy, but you take Shannon's information entropy and you multiply it by Boltzmann's constant, so it's at the same units. And you say the real entropy, the total entropy, is the Boltzmann entropy plus the information entropy. This is a really beautiful argument, because it doesn't say how you got the information. It could be as perfect as you want. And just like the uncertainty principle, no matter what you do, if you use this addition, that's the change in entropy, okay? And this generalization all of a sudden generalizes statistical mechanics, non-equilibrium statistical mechanics. This trivial addition of what we knew about information entropy, say it's the same, put it in the same footing as Boltzmann energy. One last little bit and I'll go. During the time in the 1950s, 60s, and 70s, Landauer and then Bennett began to think about what's the minimum amount of energy you can do to make a computation. And just like Carnot, they said it's got to work at a finite temperature. How low an energy can you actually get? These are physicists. And what they found was you can actually make reversible computation, which means no energy, no net energy expended. This is magic, okay, at any finite temperature. But they said, but you do a computation, you need memory. And the act of looking changes the entropy, okay? So the full computation of numerics plus looking at it means that there's a minimum entropy needed, and for 1 bit of information, it turns out to be not very much, 10 to the minus 21 joules. Very recently, a member in my department when I was at Bell Labs, who's now a professor in electrical engineering at Berkeley, Jeff Boker and his associates looked at this and the Landauer limit. The Landauer limit is these black dots. You go higher and higher in temperature, and here's his data points, and you're approaching the Landauer limit. Amazing. So this relationship between information, entropy, and everything is now being put on solid ground. And unlike what Charlie Cattell said, that entropy is really some fictional thing, it's actually quantized. The minimum entropy of 1 bit of information is KT log 2, end of story. And so all this stuff is now measurable with this biological system. Sam Peng, who did the lion's share of the analysis and the realizations with me in the time of COVID, is now a professor at MIT. These two people are professors at Fudan, and Marty just left and is now becoming a professor at Washington University in St. Louis. And Jerry Axelrod is the person who's in the acoustic oscillation box and got all the electronics to work. That electronics, by the way, is much quieter than anything you can buy. And it costs about $100, and it's transferable. Because a graduate student, I said, I want to learn electronics. He said, okay, solder this, and you know, tell me how it works, or teach the group how it works. And that's how it works. We have other associates. Of course, NIH wouldn't fund me. No one would fund me because I didn't do the work. And so we got seed money, and finally the Gordon Moore Foundation funded me. But after it all worked, then they funded me, because that's the way the US government used to work. Thank you. It doesn't work as well.
Thank you, Professor Chu, for very impressive presentation. I like it so much. It's our distinct honor to invite Professor Robert Taryang to the stage. Today, his talk is Some Thoughts on Algorithm Research. Please join me to welcome Professor Robert Taryang.
Thank you. My intention this evening is to take us in a rather different direction. I don't want to say anything technical. I rather want to reflect on some ideas of how to do research that I've developed over my 50-year career or something. But first, let me say something about design of airplanes, because this is very interesting. You know, if you think about fluid flow over airplane wings and fuselages and so on, traditionally you build a model, you put it in a wind tunnel to study this process. What's going on here? You got the Navier-Stokes equations, which are a partial differential equation that tells you how the airflow proceeds over the wings and the fuselage and so on. Rather than using a wind tunnel, you can do a computation, a very expensive computation in a computer to figure out what the wind flow is. So Navier-Stokes equations are continuous. You have to discretize the problem to be able to solve it on a computer. So instead of having this three-dimensional model of air, you chop up the space either into little cubes or into little tetrahedra in 3 dimensions, or if you're dealing just with the surface, it's 2 dimensions, so you chop things up into little triangles. If you chop things up into little triangles, you have some kind of graph structure. If you chop things up into 3 dimensions, you also have essentially a graph structure. And you need, so you can set up local equations on the little components, the triangles or the tetrahedra, and then you can do the computation in the digital computer, and all the computation is local. So you compute a value at one point and it affects the local values at other points. So you have a graph structure on which the computation is taking place. So now we're getting into the realm of algorithms. How do you do this computation efficiently? You chop up this complicated graph into pieces somehow in such a way that the interaction between the pieces is localized and very small. So subdivide and then subdivide pieces and subdivide those pieces and so on. And with the appropriate subdivision, you can then extremely speed up the entire computation. So this question of dividing graphs up efficiently into little pieces, this is something that I looked at with Dick Lipton a long time ago. It resulted in the planar separator theorem, and there are generalizations to more complicated kinds of graphs into 3-dimensional surfaces and so on. So it turns out that graph theory, which may be, and graph algorithms, which you might think didn't apply to computing airflow over fuselages, turns out indeed to be relevant. So that's all I have to say about technical things. I'll try to keep this short also. I just want to make some general comments about algorithm research, and particularly in computer science. So as I think I've already said, computer science is very young. It's maybe 80 years old, unlike physics and mathematics. And we have developed over these 80 years many beautiful, theoretically efficient algorithms and data structures. But of course, it was a problem-rich environment, so we plucked the low-hanging fruit, and we've often settled for the first good enough solution. So I think here's another thing that I have already said. The design space for algorithms is rich and becoming richer as a result of computers becoming faster, computer memories becoming bigger. We got multiprocessors. We have all kinds of things that allow us to increase the design space. So my conclusion is, in current algorithm research, we should explore the design space systematically, not settle for the first solution, but try to figure out what in fact is the best possible solution. Now let me say something about theory versus practice. So I'm a theoretician, but I like to see my ideas working in the real world. How do we measure efficiency? Well, what I have mostly done is to look at worst case running time as a function of the input size or of some parameters having to do with the input, ignoring constant factors. The nice thing about ignoring constant factors is you make the analysis machine independent, and you simplify, you reduce the technicalities of trying to get a good analysis. Is this reflected in the practical performance of algorithms? My colleagues, and even me from time to time, have relished theoretical results, but results that give us complicated and impractical algorithms. I think we've maybe overemphasized complexity at the cost of practicality and practical efficiency. So my view of the role of experiments is they validate practicality. If you design an algorithm, maybe you should actually try to implement it and run it even on small data sets. Among other things, you can reveal bottlenecks, you can reveal the hotspots. Maybe this tells you what parts of the algorithm you should improve to try to make it better in practice. And beware of over-optimization. You may optimize things you don't need to optimize. And don't take small differences in performance too seriously. I've seen a lot of papers that compare different algorithms on certain data sets, and people draw conclusions based upon small differences in performance, and I think this is a dangerous thing to do. As I mentioned in my talk today already, my goal is simplicity in my research. So we want to identify the simplest possible efficient methods to solve basic problems. Again, Paul Erdős, who was a well-known mathematician who was a font of problems, had this idea of algorithms, proofs from the book, proving a mathematical theorem with the best possible proof. Let's think about this idea and apply it to algorithm design. We want the algorithm to be simple. That is the artifact that's going to be run on the machine. We're willing to tolerate complicated analyses, complicated proofs of correctness or complicated proofs of efficiency, as long as the algorithm itself is simple. There is a temptation, because the analysis is complicated, we have to, and maybe we can't analyze the simple algorithm, we make the algorithm more complicated so we can do the analysis. That's kind of a dangerous thing. Einstein said, maybe, make everything as simple as possible, but not simpler. And sometimes simplicity is critical, not just desirable, notably in concurrent algorithms. So I didn't talk about concurrent algorithms in my earlier talk, but concurrency is obviously extremely important in large language models and GPUs and so on. You have massive parallelism going on. Our conscious thought process as human beings seems to be more or less one at a time, sequential, but we can design algorithms for computers where we have multiple processes interacting. And these algorithms notoriously are very difficult to prove correct, let alone get a good analysis for. And if the algorithm is not simple, proof of correctness becomes hopeless. So this is yet another reason to try to keep things as simple as possible. Given a problem and you don't know the answer, work on both sides. Maybe your hypothesis is wrong. Maybe the theorem you're trying to prove is not true. Look for counterexamples. If you look for a counterexample, maybe that gives you ideas about where the bottlenecks are to get the proof right. That's the way I solved the analysis of the disjoint set union problem, by assuming that the result was not linear time, that in fact it grew with the size of the problem. I got the lower bound, and then it took a long time to prove a corresponding upper bound. I think I tell my students whenever they're working on a problem, you got to look at both sides, and you get information from studying the false answer to help you solve the real problem. And of course, the question I always get is, give me a research problem. The hardest thing is asking the right question, formulating the right problem in the right way. It's at least as important as solving the problem. And the best questions are the ones you come up with on your own. Not only do you want to ask the right question, but if you get some kind of a solution, you want to try to generalize it, extend it as far as possible, build theoretical frameworks and sets of techniques. For example, the idea of amortized analysis that I already talked about, depth first search and other kinds of graph search, various kinds of data structures. I start out slow, but I try to go deep into problems. If you really want to go beyond what has been done before, you have to really get into the problem and think about it and study it from all sides, and then step by step you make progress. I think there's a lot of pressure to publish. When I was a grad student, I had a couple of papers when I got my first job, but these days it seems to be a challenge. Everybody wants to publish lots of papers so they can get a job. But you know, the results that are important and the ones that get to remembered are some very small subset of the vast universe of publications. So this is worth keeping in mind. Take some time. Read the literature, but read it skeptically. Don't trust any existing results unless you've gone through the details. Try to prove things for yourself. Try to ask what is missing here? What are the possible generalizations? What kind of new questions does the work suggest? And sleep on your results. Write them down carefully. Don't trust them until you have carefully verified them. I'm quite proud of the fact that I only know of maybe 2 published papers of mine that have incorrect results. Everybody makes mistakes. Better if you catch your own than if somebody else does it for you. Here's an interesting, I'm going to close with this. What is computer science? So people have said that anything that is called a science is not in fact a science. Social science. Knuth is writing, has written many volumes, 3.5 volumes so far, The Art of Computer Science, the art of computer programming, sorry. So he views computer programming as an art. Creative process, yes. My colleague, Bob Sedgwick at Stanford, thinks this is not the right view of what is going on. It is a science. We implement an algorithm, we run it, we experiment, we get feedback, we make a hypothesis about it. It's more like a scientific process. We're using the scientific method. Is it a branch of mathematics? What I do is proving theorems about the correctness or the performance of algorithms. It is definitely some kind of mathematics, and being a theoretician, I want it to be rigorous mathematics. Is it a branch of engineering? We're writing programs that we want to actually run on the computer and get some results for somebody that will give them answers to real world questions that they're asking. I think it's pointless to argue. I think computer science is in fact all of these. It's like the story of the elephant and the blind people looking at the elephant. So I'll let you reflect on all of these questions, and thank you for your time this evening.
Thank you, Professor Torian. Ladies and gentlemen, it's our distinct honor to invite architect of China Airplane Authority, Professor Guanghui Wu. His keynote speech will be Beauty of Large Aircraft Engineering. Please enjoy me to welcome Professor Guanghui Wu.
Good evening, dear guests and ladies and gentlemen. It's my honor to be here, to share our large aircraft. But I still feel a little nervous because I face the scientists and the professors. I'm the engineer, so a bit nervous. Anyway, I talk about the C919, some stories. So my topic is the beauty of a bigger aircraft engineering. Okay. So the flight is a dream of centuries for human beings. It is a scientific pursuit engraved in the records of the civilization. The brush strokes in Dunhuang flying to space mural carry the longing to chase dreams across the blue sky. On the remains of the Wanhu rockets during the Ming Dynasty bears the determination to soar to great height. On that morning in the 1914, Florida, when 20 generals flying across the 34 kilometers straight with a passenger, no one would have imagined that this 20 minutes journey would birth the industry that will change the world. It proved that when imagination and scientific principles merge, the borders on land can be written in the sky. The airplane becomes the first worldwide web, bringing people, language, ideas, and value together. A century of aviation history is, in its sense, the history of application of basic science. When Sir Charles Smith flew across the West Pacific Ocean in 1928. It announced that the world is getting smaller. The establishment of an International Civil Aviation Organization, ICAO, in 1944 embodied the consensus of global aviation and global harmony, with their vision of achieve the sustainable growth of the global civil aviation system. The supersonic flight of the Concorde in 1976 marks the miracle of science and engineering, a miracle of arriving before departure. The maiden flight of C919 in 2007 was yet another scientific answer to safety, economics, comfort, and sustainable aspects of the high-end communications commercial products by the Chinese scientists and engineers. We did not rely on methods, but on the accurate calculations, mastery of technology, and seamless integration of the systems. When designing the C919, we often said the sky is the tallest examiner to ensure best flight performance on airplane high in the west sky. The aerodynamics design team adopts extension safety computational analysis combined with a human in the loop, fine tuning and optimization, countless wind tunnel tests facing the dialogue with the air. Actually, with the CFD, we reduced the wind tunnel test almost more than 5% than our before to the aircraft design. Another story about the aluminum leasing alloy in the C919's fuselage hides the secret about atom and basic science. Material scientists spend years observing alloy crystallization on the microscope, contemplating how to ensure lithium atom evenly distributed in the aluminum lattice, like processing placed rivet, which both reduce weight and enhance the strength. It taught us that the materials science is never about luck, but about understanding the language of atom and the language of science. We design the aluminum leasing with our partner almost about 10 years, from the static stress to the fatigue and tolerance allowance. Finally, with the production process, so almost 10 years get a proper materials in the aircraft. The flight deck is the best office in the world. The development of a fly-by-wire system is a handshake between control theory and engineering application. I hoped the plan we designed can be as easy as playing video games, with converting pilot input into mathematics model, allow the computer to anticipate movements like a seasoned captain. A pilot shared the C919 flight deck. The side stick doesn't feel as tough and rugged like traditional planes, but with some visual room. Behind this, the engineer coding human habit and feel into the software. This philosophy of technology adapting to humans is the original aim of applying basic science into the engineering. In fact, who fly the C919 pilot, including the West from YASA pilot, say the C919 is easy to fly than others. This is getting from the fly-by-wire control role and the system integration. Okay, the collaboration started in 2024 between Beijing Institute and Mathematical Science and Applications, BIMSA, and COMAC. It's not just about futuristic technology, but about solving today's challenges and charting tomorrow's path of development. Right now, mathematicians at BIMSA are experimenting with differential geometry optimization methods to design continuously defaultable wings using topology optimization for the wing shape and using biometry to place every structure rib where the stress is highest, like a lateral bone. This mode of math directly applied to engineering is setting R&D on the right path. The technology we are focused on closely follow the target of making airplanes fly safe, more economic, more environmentally friendly, more comfortable, following the footsteps of AI4, the basing on maintenance amount of test data analysis. We have achieved 东方御风 and 东方翼风 AI for field simulation models. Next, okay. AI 2D supercritical airfoil design agent and advancing on 3D aircraft on engine impacts and 3D wings, freeing the R&D teams to focus on deeper innovation, where AI enables teams to be more agile and efficient. Speaking about the future, we emphasize more on accumulating scientific foundations. For instance, zero carbon flight, safe sulfur energy storage, optimized hydrogen fuel cell, energy conversion rate, no altitude economy, and multi-disciplinary urban transportation. These efforts might take 10 years or longer, but every step taken is close to the target. Just like our large airplane Spirit process long-term decision, long-term overcoming, long-term handship, long-term cooperation. We need the determination from the generation to the next. Large aircraft industry requires the patient breaking down great virgins into current scientific question and answer them with them and effort. I am an aircraft designer, but also a pilot. I got a commercial aircraft license. Also, I can fly the A320, C919, and the AirJet 21. And also the first academician pilot. I have gathered a cloud from the C919 flight deck. Those seemingly soft clouds are, in truth, aerodynamics exams as the bridge built between science and engineering. I have learned that large airplanes are not a miracle built, but certainties calculated from airflow simulation in wind tunnel to atom arrangements in material lab, then to the logarithmic automation in computations. Every step proves the basic science is not an inverted tower in the sky, but firm ground then airplane take off from. Okay. That's my presentation. Thank you.
Thank you, Professor Wu, for your very nice presentation. Ladies and gentlemen, now is time for dinner. The buffet banquet will be at Hall B and Hall C. After the dinner, please come back for other event. Have a good dinner. ladies and gentlemen, welcome back. So we move to next event. I now invite attendees of FSA to deliver the accepted presentations. It's my great pleasure to invite Professor Yang Lu to stage for your delivery.
Okay, good evening. It is a great honor to be here today. First, on behalf of my co-authors and my collaborators, I would like to extend our deepest gratitude to the International Congress of Basic Science, to Professor Yao, and to the selection committee for this profound recognition. This honor is especially meaningful to us because our work, while contributing to the advancements of information science, is rooted not in theoretical exploration, but in engineering and application. So I believe this truly underscores the inclusivity and the expansive vision of this Congress, and sends a powerful message to us all to pursue truly what motivates us, whether it's fundamental theory or engineering. Our work centers on a transformative machine learning paradigm called federated learning. This framework enables the collaborative and decentralized training of AI models while preserving data privacy and efficiency. While working at WeBank, a fintech company in Shenzhen, we witnessed firsthand that cross companies and industries, fragmented and siloed data cannot be fully utilized by AI. This fundamental challenge motivates us deeply, and we quickly recognize that federated learning has immense potential to unlock data's value responsibly. So to echo Professor Steven Chu's insightful lecture yesterday, perhaps we weren't smarter than any others, but simply among the first to look under this particular rock. I must also share that for the first 2 years, most of our papers are rejected by top AI conferences, mainly because that the concept was so unconventional and there was a significant lack of existing benchmarks for comparison. And today, reflecting on that period, I'm grateful that we didn't give up easily. Instead, we steadily improve our framework by addressing every critical comments raised by our reviewers. Some of these complex issues are so complex we couldn't solve alone, which led us to consult and collaborate extensively with our experts from diverse domains, such as privacy and incentive experts, as well as industrial partners from sectors like finance and healthcare. Together, we conceived new ideas and published further results addressing some of these fundamental challenges. So therefore, this award is also a recognition of the collective interdisciplinary efforts by everyone working in this exciting field. It celebrates the shared vision to transform the traditional centralized AI paradigm. We are deeply encouraged to keep pushing the frontier of AI. Finally, to the young researchers among us today, I want to emphasize that we are entering a golden age of interdisciplinary AI-driven discovery. AI offers a powerful new lens, allowing us to see familiar problems with fresh eyes and unlock new insights. On the other hand, basic science holds the key to solving many of these open challenges in AI. And the rapid evolution of AI means that your past experience perhaps matters less than your ability to learn, your curiosity to identify novel problems, and your drive to forge impactful collaborations. It is a skill set that you learn from your PhD training and apply repeatedly throughout your career. Therefore, do not be afraid to enter into new field or to overly worried about choosing the wrong career path. Instead, follow what truly motivates you and trust in your ability to learn and adapt while you stumble. If you do this, perhaps there is no wrong path because you will never regret the journey. Thank you.
Thank you, Professor Liu. I now invite Professor Dimitri Politsky to stage.
Good evening, ladies and gentlemen. Since this speech about personal feeling, let me start with a short story. When I first received the message about this award, I thought that this couldn't be possibly be real. You know, the feeling, it seemed so good to be true. For a while, I wasn't sure whether to celebrate or check the email headers for signs of a scam. And this led to a bit of confusion and delay on my side. But I'm deeply grateful to Professor Boenlien, whose kind and patient correspondence helped clear things up. And his messages, always thoughtful and helpful, made me feel welcome, even while I was unsure about travel plans and logistics. Thanks to him, I'm finally here tonight, and it's a great pleasure and honor to join you all. Now, a few words about work that has been recognized. The paper we were awarded is the result of deep collaboration, a team effort that brought together ideas from material science, optoelectronics, and machine learning. The core idea was rather simple. What if the image sensor itself could think? Using reconfigurable 2D semiconductors, we developed a photodiode array that doesn't just see the images, but processes it in real time. It acts as a physical neural network, performing computations as the image is being captured. We demonstrated not only classification, but also encoding, denoising, and even ultra-fast real-time recognition with processing speeds reaching 20 million operations per second. This work is a small step towards a future where machine vision is faster, more efficient, and closer to how biological systems function, and where 2D materials play a key enabling role. Being recognized with this award is not only a great personal and professional honor, it's also a powerful reminder of how vital recognition is in research. Awards like this are more than just a moment of celebration. They are a message to all scientists, especially early career researchers, that bold ideas, hard work, and persistence truly matter. They help us move forward with new confidence, to keep asking questions and to keep believing in the impact of fundamental science. I want to thank my collaborators and my scientific advisor, Professor Thomas Müller, as well as the broader scientific community that continues to inspire and challenge us. And finally, thank you to the ICBC 2022 committee for this incredible honor. I'm truly grateful and look forward to continued dialogue, exchange, and progress in this exciting field. Thank you.
Thank you, Policy King. I now invite Professor Rainer Sprick to stage.
Thank you. Good evening. It's really a great pleasure being again here in China, in Beijing. I've been many times in China. It's the first time for me to accept an award on behalf of our team. And we're really grateful for this award, which really rewards our work on using robotics in scientific research. Really want to thank the organizers of the conference, ICB conference, the committee that did the selection, and also Professor Yao for this event here today. In chemistry, there's really a clear need to develop new tools to do research. And in a way, I really envy biology, which has really made significant advances in terms of the tools that they use. As an example, if you would take a chemist from the past 150 years ago or so and put them in a lab today, they would, broadly speaking, recognize many of the tools. Take a biologist from 150 years ago and put them in a lab today, they would really struggle and not recognize very much. But we really need advances in materials chemistry to address really quite diverse and important challenges. In chemistry, there have been new approaches such as high throughput already being used, but mainly really relying on tracked systems, therefore really large stationary systems that are also very expensive to use. In the paper that's been awarded this prize, we use a mobile system. So rather than having a system that's fixed in place, we use a system that can drive itself in space and use machines that are really standard equipment in the lab. So it really enables a much more flexibility and using cheaper equipment for similar work as well. This really allows us as well to access a large experimental space that can be covered, and really also to enable new research which might be otherwise deemed too risky or too expensive. This project really needed guidance from a lot of people, a lot of contributions, expertise in automation, of course, in AI, in computer science, and also, of course, the chemists as well. So really, it's quite an important team effort that could have not been done by individual parts of the team. We have also, of course, funders. LeverU was really instrumental in funding this project, as was UK Research Innovation Council. We hope going forward that we can address some of these important challenges, for example, in sustainability, battery research, carbon dioxide conversion, or maybe plastic recycling as well. I also want to echo what some of the other speakers at the main event said as well, that collaboration is very, very important, and really particularly international collaboration can be really, really enabling, particularly in these difficult times. You should focus on that even more so. With that, I would like to thank you for the prize again, and thanks very much.
Thank you, Professor Sprick. Now is the time for panel discussion. The host is Dr. Zhou Yanquan, and we have 3 academicians invited, who are Professor Steven Chu, Professor Robert Yang, Professor Guanghui Wu. Now I give floor to Dr. Qian.
Ladies and gentlemen, tonight is really special. We are right here where science meets real-world engineering. I'm the host, Zong Yanqian from COMAC. Just think, when Professor Robert Young's algorithms work like perfect gears, quietly running massive engineering systems, when Professor Steven Chu turned laser cooling theory into a tool that actually measures stars for navigation, when chief designer Wu Guanghui used brilliant systems engineering to lift China's own big passenger jet into the sky. That's when we truly see it. Basic science is the source code behind every engineering wonder. So right now, let's put our hands together for these three trailblazers. They have lit the way with Nobel Prize brilliance, Turing Award genius, and game-changing national projects. Join me in welcoming them as they dive into a crucial question: how does fundamental science become innovation's secret weapon? I have a couple questions for our panelists. The first question is for Professor Chu. Does engineering have to wait for science to be fully figured out?
Absolutely not. Quite often engineers, especially material science engineers, which are very complex and very hard, there's no really good theory yet to predict complex properties of materials or even molecules. And so they don't wait for scientists. Quite often they discover something new and then the scientists try to scratch their head and figure out what's going on.
Okay, great, thank you. And I have the second question for Professor Taiyang. How do you see the back and forth between the basic science and the urgent engineering needs? Is it a step-by-step process, or do they actually boost each other?
I think engineering and applications interact in a constructive and somewhat chaotic way with theory. There's definitely a back and forth, and which one determines the other just depends upon the circumstances. It's an interesting process, but if you're a theoretician like me who was interested in applications, you look at the applications and see if there's something you can bring to the theory, bring the theory to the application. And if I have an algorithm, I put it out there for the world, and if people can pick it up and use it and experiment with it.
Can you give us an example?
Well, for example, the splay trees that I talked about in my lecture, self-adjusting search trees, it's a simple data structure, and it has been used in practice quite heavily because, in fact, the worst case doesn't arise so much. You need something that adapts to the situation. And it's so simple and it's so adaptable that it has been used fairly widely in practice. And in fact, we got another award for this very thing. There's something called the Paris Kanellakis Award for Theory and Practice that's given by the Association for Computing Machinery. And Danny and I got this award because this data structure designed on the basis of theoretical principles and turns out to be useful. And I think it goes the other way too, just as Steve was saying. People run things in practice. People run algorithms that they don't necessarily understand, that work empirically. And our challenge is to try to provide some theoretical understanding. And maybe then the theory contributes to improving the algorithms.
Okay, great. Okay, thanks. So I have the third question for Chief Designer Wu. If you could pick one area for basic science to make a breakthrough and solve your toughest engineering challenge, say the aircraft design, what would it be?
Okay, I try to answer in English. we can't divide the science and engineering because the engineering based on the science, such as mathematics, many computerized based on this. So I just told this afternoon about the C919 design. The CFD is based on the mathematics. It's, of course, it belongs to the science. But we use it as an engineering tool to design the supercritical wing. For each section, the airfoil, we designed almost 10,000 sections for airfoil. Gather together more than 100 engineers, some from like Tsinghua University and the Beijing University and Northwest Polytechnical University and also Nanjing Aerospace University. We divided some teams to individually design and get together with computer safety. Then finally, we use the wind tunnel test for select which one is best. So then we second loop use these results to design a new airfoil and a wing. From the science, we hope for example, the pressure display, pressure, how to say that, the division, pressure displacement, we need the smoothly curve. But actually, we cannot reach the science design because somewhere we have a little bit supersonic flows in the top area. So we just choose the balance for the high speed, lower speed. So it's not the best design, but it's coordinate. It's suitable for our airplane. So those the engineering and the science is very complicated. It's closed, very closed. So choosing in the future, I think we will use the safety for the drug, because the drug is most difficult to process, to calculate. So next, we want the safety for the laminar flow or turbulence flow. It's a weather or supersonic, subsonic flight. Maybe we will focus on the drug, on the transonic airflow with the science and the mathematics and the safety computer to simulate many cases. Finally, we use the wind tunnel test to prove it.
Okay, thank you.
Thank you.
Yeah, it's pretty good.
Okay.
Good. Yeah.
I know very little about airplanes, but I have a question. In the simulations, what we teach freshmen in physics is just pure fiction. It has nothing to do with laminar flow across a curved surface. In fact, it's very much, in the end, it's a turbulent flow directed downward to create lift and how to minimize that. My question, though, is those little winglets, it took people a long time to realize that those things can reduce the turbulence and drag at the end by doing this. Why did it take so long?
Oh, you mean the
at the wing, the little
wingtip?
Yeah, the wingtip.
Wingtip, a small wing.
Yeah, the small wing.
We call it small wing, wingtip, a small wing. Because the lower surface, the pressure is higher. Up surface, the pressure is lower. And when the wingtip, there will highest pressure area through to the low pressure area. That's make the...
No, that we understand, you understand far better than I do, but why did it take many decades
Oh, yeah.
to decide that if you just did this little thing, because anyone who does Navier-Stokes by computer, Navier-Stokes is very complicated, you know, and so why did it take so long? Because they could start fooling around. And, you know, good engineers can fool around and try. It's like scientists, we fool around. Computer scientists.
Yeah, but if you have an airplane, you don't want it to crash, so you got to be careful with your fooling around.
Oh, no, I know that. but yeah, you don't want the wingtips to fall off. But you know, but they retrofitted all. It was so good they retrofitted all the planes.
I think it's probably
there are different ideas about the wingtip. There's different ideas about the wingtip. Someone says it's not contribution much. It's just a concept to reduce drag. Somebody believe it can reduce the drag. So you see the many places, some airplane have the wingtip, but some no, such as Boeing 777, there's no wingtip. So almost the Airbus, when they are wingtip, there are wingtip on the airplane.
Your plane had a wingtip.
Yes.
And we have it, yeah. Yes.
Yeah, I think the wingtip is probably a good idea, but I think there's probably two reasons. One reason is, you know, the aircraft people is always very conservative. You know, they are concerned for the safety, and the second reason is probably they didn't really believe it's too good to be true. You know, yeah. I talked to a Boeing people about this. Yes, yeah, it's probably another reason. Yeah. So, Professor Chu, I think you have had a lot of experience working with scientists, researchers, and engineers, right? What kind of teamwork across, you know, the fields, say between those guys, the scientists, researchers, and engineers, is the most critical for turning science into urgent fixes for big challenges?
I think the most crucial part is that the scientists and engineers really have to work together, not hand off or say, you know, here's a problem, we'll go solve it, but to really work together. But the difference between science and engineering is very fuzzy. For example, if you look at the Juno neutrino detector or particle accelerators or the radio, you know, 500-meter radio, you know, this is huge engineering. And even in my own laboratory, if I think about what I need to do things, to do science, a lot of it is serious engineering. And so most of the time, in many parts of science, you spend most of your time engineering the new thing the motivation is basic science discovery.
Yeah.
But in order to turn it into real things, you have to do the engineering. And the engineers have a good sense, I think, and when I work with the engineers and when I was working at Bell Laboratories, and we had brilliant engineers, and those engineers, I didn't really see a difference between an electrical engineer doing laser science and a physicist doing laser science in terms of making better lasers, doing things. And so I think it's, you know, an artificial barrier. It's just sort of like whether computer science is a science and art and engineering, all of the above. This distinction is very artificial in my mind. But to answer your question, just work very closely together and bring the strengths together, but you do it by doing it every day in close proximity.
Great. Okay, excellent. So, Professor Taiyang, you know, so when you are up against tight deadlines, how do you juggle using proven science versus exploring risky cutting-edge ideas? You know, it's you know, between the using something is already proven good, you know, and something is not really, no, you know.
I think in industry, the good enough solution is the solution that people use. So I've spent time in industrial research labs, Bell Labs, NEC research, HP research, Microsoft research. the challenge for the researchers, so the difference between academia and industrial research is academia, at least in my experience, it's curiosity driven. It's driven by what you see as interesting problems. But in industrial research, there's a goal. You want to invent things that are going to help the company. But the issue is getting the research into the product. There's a barrier between what the researchers do and what the products look like. And of course, the product people, if they have something that works, they're not willing to take the research. So if you want to succeed as an industrial research, you got to identify the pain points that the product people are having, solve their problems. So you need very tight communication between the two. And the new model of industrial research, I think, is much more to embed the researchers in with the product team so you get communication going. And this may be much more effective, actually, than separating research from production.
Okay, I see, great. So I have a last question for Captain, Wu, how do we bridge the gap between the theoretical science and the real-world engineering solutions? What will really help us to do it?
Yeah. For me, it's difficult because I just said it's very closed. Sometimes in aircraft design, I think there's no gap between engineering and science. Just make the examples about the safety and also the structure design. The structure is based on the stress or the force. And also materials. This afternoon I just taught the aluminum, lithium, the materials. Last, we select the material to build the aircraft. It's called the one generation materials or one generation aircraft. But I would like to say the one generation aircraft, then a generation materials, because the materials designed for aircraft, we need the materials development. So that's very close for the science and the engineering. So, but certainly there are some differences. For example, we make a blueprint. Now it's the 3 modules in the computer. That's just the engineer doing. But it's based on the science and their knowledge. So it's just another question is the engineering. Just we have a time scale. So maybe science maybe take a longer or no such focused deadline. For the aircraft, we have a deadline. We say the deadline, the burn chart. So reach the market requirement. So I think it's from the management is different from the science and the management and the engineering. So
okay, excellent.
That's my question. That's my answer.
Okay, thank you.
Thank you.
Now we have 10 minutes for the audience to ask questions for these 3 big professors. And is there anybody want to ask questions? Oh, yeah. Maybe this one. No further innovation.
Thank you for the fabulous talk, for sharing. And I got a question for Professor Robert Taja. And as we know, we do have a very famous and open question as NP versus P. That's talking about if there are any, algorithms can verify the solutions in, say that, in polynomial time. And I just wondering, do you have any opinion regarding this question? Thank you.
Well, that's the most. So the question concerns my opinion on the P versus NP problem. So let me just tell you all what this is. So back in the late 1960s, while we were working on very efficient algorithms, Jack Edmonds was an operations researcher, did beautiful work on matching algorithms and network algorithms. And he had this notion of an effective, efficient algorithm versus a situation where you can verify the solution. So if we think of, for example, the traveling salesman problem, which is we have a graph, we have edges on the edges, lengths on the edges. We want to find a closed, simple curve that visits all the vertices at minimum total cost. This is a traveling salesman problem. It's a trivial problem from a mathematical point of view because it's finite, but there are an exponential number of possibilities. If I set a cost criterion and I give you a solution, you just add up the cost of all the edges and I can say this solution meets the cost criterion or not. But if I don't provide the solution to you, but I give you a cost criterion and I ask, is there a tour with the cost at most this much? You have to do this exponential exploration. There are many problems that seem to require exponential exploration, but if I hand you the answer, you can easily verify it. So this class of problems where it seems like you need to do exponential exploration to verify the solution versus I hand you the solution, verifying is trivial. This is the class of NP, non-deterministic polynomial time. So the question is, are any of these problems, or are they all, can any of them be solved in polynomial time or not? That's the P versus NP problem. I think most of us in the field think that the answer is no. It would be a very strange world if the answer were yes. I hope to see a solution in my lifetime, but this is the classic, famous open problem in computational complexity. Sorry for such a long-winded answer.
Okay. So anyone else? Yeah.
Okay. I have a quick question for Professor Guanghui Wu. Actually, you know, the fusion of the technologies, including the green technologies, intelligence technologies, and even the robust security technologies is the kind of transformative driving force across the industries. And for the COMAC, actually, you are designing the larger aircraft passenger jet. How about the challenge for the low altitude economies and for the dual energy airplanes? How do you think? And 我是想这个现在这个所有的这个技术的结合，会是我们各个工业里边是做这个创新的一个 driving force。但是我们现在做了大飞机了，对于现在这个绿色技术啊、智能技术的结合，对我们新能源飞机会对我们这个带来一些什么主要的挑战？好，谢谢。
So my question to that, as I understand, the combination of a series of advanced technologies have been the driving force for industrial development. For example, the adoption of green technology, is it gonna to influence the design of the aircraft to make it more environmentally friendly? Thank you.
好，这个问题是，哎呀 ，sorry， 也走神了，是，哦 ，OK， 这个 ，sorry。For the future, I think the SAF, it's the main solution for the low emission. That's right. So the new technology bring the aircraft design the forward. For example, the past, the aircraft developed just in the aero area is just the aviation industry. But in the future, they will combine. It's not the aviation industry or aviation technology, but in future we should mix with such as AI, such as the green development, green, and also even the atmosphere for the navigation for satellite navigation, radios. So it's many disciplines mixed for and together for support the aircraft development. In future, no doubt, it's rarely the aircraft that combines many displays. So that's it's not a simple aircraft. It's not that 100 years ago, 1 or 2 persons could design the airplane. For the modern airplane, there are thousands of hundreds people, engineers, working together to make a modern airplane. That's sorry.
Thank you, Professor Wu. Thank you.
Okay, thank you. We'll take one more question.
This question goes to Steven Chu, Professor Steven Chu. But if the other two the distinguished scholars care to answer, that would be great as well. My question is about AI. And nowadays, it is a very, very hot area, hot topic. By AI, I'm referring not the automation plus, not as a tool that help us in terms of improving our productivity. I'm referring the possibility of a real AI with intelligence. So the question has twofold. The first one is, do you think that a superhuman AI with superhuman intelligence is achievable in a, let's say, 10 or 15 years time framework? And the second part that goes with the question is, as someone with your unique experience of working both industry lab, university, and also as in the government, do you feel that is there something we should be concerned about?
Well, it's really, I'm going to quote the greatest American philosopher of the 20th century who plays baseball. And he said predictions are hard to make, especially about the future. So in terms of AI right now, the way it exists now, it's mostly interpolation. It's, you know, thought completion, if you will, and going extended. The first thing is already being done is to incorporate the known laws of physics and other things that have been tested in the laboratory into that. But that's not real intelligence yet. We regard real intelligence as being able to see something, and make a synthetic leap. I was explaining in one of the talks, I think yesterday, of Newton and Kepler, and then Newton realizing, and Galileo and Kepler. Galileo actually had Newton's laws, sort of, but didn't have the mathematics. And then realizing that the pendulums on Earth and planetary motion were the same. Big intellectual leap. Another intellectual leap, general relativity. Those things I regard as really big intellectual leaps. Then it's hard to predict when intelligence can make that dramatic leap, to look at it completely differently, turn it upside down on its head. If I use ChatGPT or Perplexity or any of the things now, they always give me sort of little perturbation answers, or they look at what is in the literature, and if it doesn't hallucinate, actually a little hallucination is good. among
Maybe.
basic scientists.
It depends in what setting.
Well, by hallucination, you
If
you
your
need,
AI doctor is hallucinating about the responsibility of what your symptoms are.
no, when you're treating people, when you're designing airplanes, you don't want to hallucinate. But if you're designing algorithms, sure, because you can test them, and same with science. And so I regard the real intelligence, to go to the heart of your question, is be able to not just synthesize from one field and another. That will come pretty quickly. But to really turn it upside down and on its head. The way Einstein did relativity, it really turned things upside down and on its head, especially general relativity. But with a very simple idea. If you're in a sealed rocket and you're accelerating, you can't tell the difference between that and a rocket on Earth, and you feel 1g acceleration. And from that, the whole concept of geometry and how mass, this is remarkable. It will happen sometime, but I don't know when, because anybody who tries to set a boundary difference between human intelligence and machine intelligence, it's a slippery slope. First it was chess. You can never beat a grandmaster. Then it was Go. Oh, that's a much more complicated game. And a little bit later, it does that. So you see this watching it. And so in the end, hey, we're sort of kind of a machine too. And there's, all the circuitry and things like that, very different architecture, but it's still there. And so it will happen, but the thing that all you young people, don't worry about it. If you have the imagination to do something a little bit out of, completely out of the blue, you will always have a job. You will also always have a job because robots are too expensive. They're much more expensive than graduate students and postdocs. But it's a very cynical set. But in the meantime, the human intelligence, I still has a long way of going. Now, the threat, remember the movie 2001? Hal, that computer said, Dave, what are you doing? Dave, you don't want to do this. The threat is not, I was thinking cynically, well, you can unplug the machine. But what you can unplug is your dependency on the machine. And if you become too overly dependent to have the machine think for you, that's going to be really dangerous. And so you have to think for yourself. You use it as a tool. Like we use a calculator to do square roots. When I was young, we had to do experiments manually. So you can lift them and you can do other things. But the real thinking, you still have to do. And I'm a little bit afraid, but people get intellectually lazy. And they let them do the writing for them. They let them do the research for them. Okay, then it's a real danger. But, and if you're so lazy, and if you're a student, you want to avoid this stuff, then you have to ask yourself, why are you a student? Why are you doing this or that, right? Of course, you can say, I want a job. but I'm both optimistic and pessimistic, mostly pessimistic about the dependency on machines to do your thinking. Very different than using a steam engine or an automobile instead of a horse, right? And you can say I'm dependent on an automobile. In America, that's sadly true, and maybe even Beijing. But so we'll figure out a way to survive. But it's going to be a brave new world. I don't know. I mean, should ask him.
I'm tempted by what Professor Lustig said, which is essentially
Things that are out of my area of expertise, I don't comment on, and I'm not an expert in AI, but I do have an opinion on this. Obviously, it's a very hot topic these days, and there are the people, including Eric Schmidt, who I heard give a talk recently at the 100th anniversary of Bell Labs, who thinks in 2 years comes the singularity when computers are going to be smarter than people. That's an extreme point of view. I disagree. I think it's going to take a lot longer. I worry about the dependency issue, especially in our teaching. How do we deal as academics with the fact that if you give a standard kind of problem, the student feeds the problem to the system, and the system solves it for them or writes the essay or whatever. To all you students, don't get lazy. The dependence issue is a big one. But I also think these systems are missing something fundamental. This is artificial intelligence. This is not natural intelligence. And what is the difference? Very young children are active and curious about the world. They explore, they investigate, they try out things. I think these systems need to develop this kind of proactivity, curiosity. I think that's an important missing element. And I also think we have to find some way to train these systems to have some concept of ethics, morality. We have a hard enough time with human beings training an artificial entity and whatever morality is. This is a big challenge, but we had better get this right. And we better think about it before these systems become smarter than we are.
Okay, thank you. So the AI is actually very hot. We can discuss it, I guess, in the future again. So thank you all for today. And I think we started the panel discussion with the relationship between the basic science and engineering, right? And we then go to the wingtip, and then we go to the AI, new energy aircraft, and also the polynomial, right? So I think we have some big takeaways, right, for today's discussion. The science isn't just engineering's instruction manual, it's the living, breathing source code. And engineering is not just applying science, it's asking science the next big questions. So let's have a big applause to our incredible panelists. Professor Taiyang,